Nope. It's mine.
Just give it to me.
Okay. You have 10 minutes to demonstrate your solution and make a quick explanation of what happened, how you got to that problem and that solution.
Does it work like that?
Yes. Oh. Weird. Okay, 10 minutes.
Good evening. My name is Javier Mejia, and my teammate is Michelle Ochoa. And today we are going to present to you our final project for data structures and algorithms. First of all, what is the problem and what relevance does it have? Well, the consequences of misuse of data structures can lead to various problems, and some can be so severe that in some cases, such as the hard security vulnerability, it can make users to have the access to confidential data within memory, which is terrible as it can lead to some unforeseen consequences. Also, the Night Capital Group website crash, which caused huge financial losses due to a faulty tracking system process. Or performance problems in databases due to poor indexing and normalization, which we are mainly targeting right here. And our project aims to efficiently search for information within extensive data collections through the use of the right data structures and to perform operations such as adding, removing, storing information, searching information, and also printing it. So now, the current approaches that are available are some of these Python libraries, which are Pandas and SQL Alchemy. Pandas is a very well-known Python library that provides data structures and data performance analysis to work with huge amounts of data and to efficiently manipulate it. And the main data structures that it uses are data frames, which are like two-dimensional structures similar to hash tables, and series, which is a one-dimensional structure similar to arrays. And what both of these have in common that we also need is the flexibility for the data that can be handled. With SQL Alchemy, which is also a Python library that allows interaction with database structures, it uses metadata, which is used to keep metadata information organized in rows and columns. Tables, which you can access and define conditions under search, and columns, which define columns in a table and the data type it will store. As for the stakeholders and opportunity that our project offers, the primary beneficiaries of our solution are programmers and data analysts alike, as they work with data and in many cases with large amounts of data, which if the data structures are not well optimized in the programs, can lead to very bad performance with bad space usage and time optimization. And it can be seen in some social networks, which are connected to databases, and music playback systems, which also have large amounts of data. And the development of this solution enhances search efficiency in a much larger scale and with large applications and programs. And It also allows for processes and memory optimization by seeking the best solution in data structures and the algorithms. And now for the data structure comparison and analysis, we thought that the four best possible data structures to choose were hash tables, binary search trees, single linked lists, and vectors. With hash tables, we found a space complexity of O2n, one space for the key and one space for the value, that is 4. For the insertion and deletion, O1 or ON, depending on if there are collisions or not, and how they are handled. In our case, we will use it with the next available space, if there are collisions. Now, with search operations, we found that also O1 or ON, depending on the collisions, you can vary depending on how the collision is. Data printing of the operations medium efficiency, as it is tabular with rows and columns, and data flexibility great as it allows for basically many types of data to be hashed and organized. Also binary search trees, which we found the worst space complexity with O4n, for the pointer to the tree node, the value in the tree, and the pointers to the left and right value. The insertion and deletion can be O log n, or depending with the size, O n, as it needs to compare values. Search operation is O log n or O n, which also depends on the scale of the binary tree. With the data printing of the operations being inefficient, as it has to go recursively within the tree nodes, and it becomes really inefficient. And with data flexibility being regular, as long as the data can be compared within each other. With single linked lists, we have a space complexity of O2n plus 1, which is 1 for the pointer to nth value, 1 for the value, was the first pointer of the list. The insertion and deletion O1, search operation ON, as the list grows. Data printing of the operations pretty inefficient, and data flexibility found to be great. With vectors, the space complexity was O(n plus 1), as it is like the best that we found around all these, but it has its disadvantages. With the search operation and the data flexibility, as it needs to be homogeneous, as vectors are stored in a continuous space of memory and have a certain size limits. And so we chose hash tables as the most suitable data structure for a solution for all the aspects mentioned, followed by single linked lists, then vectors, and then binary search trees. For the references, and now we will present to you the algorithm.
Okay, we chose hash tables because of the reasons we explained, and we deal with mainly searching in a big data collection. And with that, we have to deal with operations like storing the information in the memory, deleting, adding information, and the main problem that is searching. And so this is the algorithm that tells the user how to add. That is, when you add, first it calculates the index with a hash function, and add it and manages the collisions. And we use an order map that is a hash table in C++, and it handles the collision with a single linked list. And deleting, it needs to again calculate the index and go to that position and delete. And for searching, we use like a search it where you tell the column where you want to search the value, and then tell the value you want to search and to draw the value you want. For example, if you have, we handle it like if it was like Spotify, so you can search a song and then you can get, for example, the artist or the genre. So, for example, you can search a song called Africa and get the artist.
Children.
Here,
Mhm.
the song we search, that is the song, and the artist that is the song, and the artist that is the song. And that's how I'm doing. Thank you for listening.
Ooh. Thank you, team. Javier, say a number.
7.
7. Okay, let me look at 7. 1, 2, 3, 4, 5, 6, 7. Okay, it cannot be again you. So tell me another number.
2.
1, 2, team 7. Michelle, Javier, please complete this. Michelle, please complete this.
Well, first of all, our project, we wanted to think of something that might be useful, like every time. So we thought of a problem like larger companies could use. So we thought of that maybe if a company has too many files stored in one place, and just keep storing them, then how do you realize which ones to eliminate or which ones to keep so you have more space for the important ones or the recent ones? So this was like the base of our problem. So we decided to create a simulation in the memory in which we have a limited size, then we can add files, so if the file size doesn't go above a certain number we declare, then it will keep them. If it does go on, it will eliminate the first ones until the number is less. An application that we found about this is WhatsApp, actually, something that we use every single day. There's a function in WhatsApp that allows you to eliminate the oldest files, so your phone doesn't get overcharged of memory or all the technicians have all the photos. So depending on a certain date, it will start eliminating files until you have only the most recent ones or the more important ones. So as I said before, we have two steps to this, two main things. The memory simulation, which comprises of creating a limited size list that can only have a certain amount of items, and as well, it will also include the asset size. After that, we also created the cleaning process for storage select, which it will take, if the size actually does surpass, it will take the oldest one, eliminate it, and only keep the more recent ones in order for it to be like the more important ones first. So we as well, we had to think of the considerations that we had to do. For example, we decided to use hash maps and linking this because we thought it was the most efficient method to use. As well as we needed to think of a way to keep the program the most efficient way possible. So our program comprises of elements. As first we have the simulation part, as I said before. Then we have the whole algorithm that cleans, that eliminates. We also created two environment variables, which means that those are variables that no matter how many times you run the code, they'll always keep the value as they had after the code was previously run. So for example, if in our case you add 5 elements to your list, then when you run it again, that list will still have those same 5 elements when you start the code from scratch. You won't lose them. This way, we can fully simulate the whole memory process more efficiently in one of the accurate ways we can truly analyze it and complete our problem. As well, we have the algorithm or the input, or all the user does is input then how many files there are, their name and their size, and the algorithm works by itself. If it surpasses, it eliminates. If it doesn't, it keeps them on. Then it will print all the available files per se that was in that list.
Then we have to analyze why we're using hash map a little bit. For the most important thing for this program is the efficiency, the running time efficiency, and the memory, because we want to implement this in big data amounts, or like for example companies that manage big data. So we have to have the most efficient data structure. That's why we choose hash maps. Why? Because hash maps are easy to insert, search, and delete elements from it because thanks to keys. Thanks to keys, it's easy to search for elements in hash maps, and it's easier to insert or delete rather than, for example, the queues or trees that there are more efficient memory like data structure, like for example binary search trees, but in the hash map it's easier to insert and look for elements. And also we use linked list to get the to get the elements in the cache, inside the cache, so then we can access to that files on the code. And why we chose linked list? Because it's easy to travel in the linked list. So we can look for the elements of the files in the program. Also the main problems with this are for example in hash maps. If you don't have like a hash function well declared, it could develop for example a crash in the program. So you can lose some files or all the program or all the files. So one important thing we have to have very declared is the hash function. So we have to have it very good. So if not, if the program is going to crash. And also in the linked list is kind of a memory structure that uses a lot of resources because it has two data, the pointer to the next link, and also the data that is on each link. So it may be a limiting factor. For example, if you're working with limited resources, like in the computer you're working, or the company is not that big and it hasn't that much resources, it may represent like a limitation because it also uses the hash maps and the linked list. So the memory is going to be full if there's not well prepared the company or, for example, the computer you're working on. And now I'm going to talk about the time complexity, or like the complexity of program. So this we're using LRU algorithm, that is the last person used algorithm. So this has a time complexity of 1, so it may be, or it represents that it's very efficient and very fast compared to other algorithms. And thanks to the use of linked list and hash maps, we can reduce the time. So the algorithm or the program is very efficient compared, for example, if we would use queues for stacks, because in queues and stacks, if we would use queues and stacks to loop or insert or, for example, delete some, we have to copy a part of the stack, pick it up, take that element, and then put again this element. So that decision, I think, is what it was the decision, because it represents with algorithm, with the hash map and the linked list, we end with an O to the N time complexity. So it's a very efficient algorithm, and I think it's very competitive to other algorithms, and it's very efficient.
So as well, now we'll explain like the logic of the code, like the process it goes through. First, you initialize like the cache function, which is just the initializing the size, like the cache list per se, the memory size of the curve that's there from the get-go, as well as it will also initialize the two environment variables we declared. But first of all, it will check that if they already have data inside it, then it will pass it on. If it doesn't, it removes a 0. Then the primary loop of the whole program will start, which is it will ask for how many files there is. Then after you put the number, it will repeat how many files you put. It will ask the name and the size. Once it asks those two, it will save them into a variable, the random variable that we declared. Will save the name and the sizes to 1, and the size for itself in another one. So we'll repeat this until we manage to reach all the number of files. Once it's done, once all the files have been declared, then it will check for the total size if the total size surpasses the one that was declared in that occurred from the beginning, then it will take the oldest one. Doesn't matter if it's the one you just added or the one that was added way before that. It will take it, eliminate it, then recheck if the size still is higher than the one we declared. If it is, then repeat this process until it finishes. And then once it reaches that level, that the size is lower, it will save the remaining ones into the variable of remaining, and the new sum of the sizes into the other one, and then it will print the remaining ones in the list.
Thank you, team. Please complete this. Thank you. Aitana, say a number. 6. 1, 2, 3, 4, 5, 16, 3. Thank you. Ten minutes, Tim. You can turn the projector on that controller. It is now. Give it a couple of seconds to turn on. And you can begin whenever you want.
Nervous tick.
What?
Nervous tick. Hilarious.
Ah, it's dying.
Oh no,
Doesn't need to like.
it is turned on at the same time.
It's the
It's here,
projector.
but it's not here.
It's not.
It's sleeping.
What? Why? No?
He died. Yeah, it's right.
That's it. Ready? Set. Not ready, not set. Go.
Imagine a world where accessing data is not just fast but optimized to perfection.
Do it. Improvise.
Okay, so, imagine a world where accessing data is not just fast but optimized to perfection. Where latency is just a distant memory, and running your applications is very fast, providing the users with an unparalleled experience. This is the world that's created with last recently used cache, LRU.
So this is our computational problem. So when systems want to retrieve the same data over and over again, repeating all the same operations to get to the same data that just has been accessed, they can face a lot of problems. The main problem, the main problematic, is the latency. The latency, when is increased, it can lead to slower data retrieval and make more slow response times.
Also, the network overhead.
The network overhead is only the extra data to maintain communications within the network. Also, the computational cost. If you want to make a process from start to finish every time, it will make the process really expensive. Also, it's connected with the scalability. If you have a small amount of data and it's already slow, imagine if you have a really large amount of data. So it will be really, really slow. Also, the resource utilization that it can make the resources waste of money, time, and even your employees. So also, and maybe the most important, is the user experience. If the user is not happy with the experience that is having within your product, your service, he or she will not come back. Well, all RU is really important and it can be really useful in these cases. Databases, mobile applications, search engines, file systems, APIs and microservices, content delivery networks, and of course, machine learning and artificial intelligence.
This is our algorithm. This represents the food operation, and this is the get operation. In the food operation, the inputs are key and value pair. First, it searches for the key in the hash map. If the key does exist, it erases that entry from the double linked list. It adds the updated key value to the front of the double linked list, and it updates the hash map and its iterator to the new position. If the key doesn't exist, first it checks if the cache is full, which means if it's at capacity, if it has reached its size, and then it gets the least recently used item from the back of the double linked list. It removes it calls the remove function, and first it removes it from the hash map, and then from the double linked list. And then the new item is added to the front of the double linked list. The hash map is updated with the new key and its iterator. And in the get operation, the input is just the key. It searches for the key in the hash map. If the key does exist, it moves the access key to the front of the double linked list, and it calls the retrieve function, returning the value. The data structures that we found to be more optimal to implement last recently used cache were the hash map and the double linked list. The hash map is used to look for the key value pairs. Each entry in the hash map represents a key value pair in the cache. The get operation and pro operation have a time complexity of O1. Then in the double linked list, the double linked list maintains the order of use of the cache entries. So when you and it's a double linked list because it allows for insertion and retrieval of the nodes. Insertion and deletion of nodes. And then the preparation is also a time complexity of O1. And then in the remove operation, it's O1. And we're going to show the code. Well, these are just the declarations of the hash map and the double linked list. Here is the constructor for the class, and we have here the operation. This
this is a good operation, and we put a little application with integers.
Segmentation fault.
Okay, so here we see the first one that uses a put operation. So it inserts 1, and then 2, and 3, and the maximum size or capacity of the cache is 3. So it has already reached capacity. Then when we get 2, we retrieve the value here, and it's updated to the front of the non-linked list. And then when we try to put a 4, we cannot because it's already reached its capacity. So it removes the least recently used value, which would be the first one that we put, which is the 1. And then we can put the 4. And that's how it works. Thank you.
Thank you, team. JP, a number.
4.
4.
Oh, sure it's not you.
Team 4. It is you. Yes.
We have to evaluate. Santiago?
I don't have a.
You should put my name on those words. Oh, yes, but I put
Someone left
so,
here.
okay.
Don't write your.
Your wallet.
It's not mine. Yes.
But I don't get it. So if I put him 10, do you have to put myself a 0?
Yes.
Oh, it's a one. Sorry.
I think you're a
A little bit.
So, wait, but you don't have teams.
No.
And fucking both. So,
Ready? Go.
That's true. Okay, now we are JP, Juan Pablo, and Luis Fernando. We are going to present our final project. Well, firstly, imagine that you are in a line for buying a ticket for your favorite artist. You are in line, you have been like 1 hour there, you got earlier like 1 day, so you have a chance to get a ticket. But by no one can say that, but someone enters the line in front of you. You got angry, you have been waiting for a long time, and someone enters. And that's not only one person. In some time there are 10, 20, 50, and by the time the tickets are already done, well, they are already sold, everything. And you, even though you got 1 day earlier, you got no tickets. How does that make you feel? Well, we are going to present our project.
So, what my teammate explained is something that in this world of analyzing data and managing it, it's called starvation. So, starvation is an important thing to solve on these kind of systems that we're making to prevent stuff from happening, such as these 2 main reasons. First of all, when something gets starved inside a queue, which is like the structure we're using for managing the priorities, the elements stay inside the queue and they become bloated, they start growing in size. The more elements stay inside because the other more prioritized ones are exiting the queue. So, the more it grows, the less memory efficient it becomes, and it becomes one hell of a data structure to maintain. Both because it uses a lot of memory, so you get less space, And because the more use of memory it has, the longer the processes are going to take. Second of all, we're dealing with priorities here. So, the reason we're actually implementing the priorities is, well, because some have a higher priority, they're needed before others. So if some of them are staying inside the queue itself, that will twist the actual priority that the element is being given. And if the priority that we wanted to have will not be given the actual priority it needs. There's a lot of priorities going on here. I know. Alright, so for our program that solves this starvation, we use these main 4 data structures. This one at the top, the heap. We could say that the heap is basically the magnum opus of combining all these 3 into a beautiful soup of greatness when it comes to prioritizing elements. So let's leave it at the end. We have the vector. Pretty simple one, yes. The vector itself, it's not really built for prioritizing stuff, but it's very efficient when managing memory. It doesn't really need much to get to the element you want, because it has an O of 1 for searching elements. You can do random access, so you can get to any element in the vector without doing much stuff. And yeah, you can resize it if you need to resize it because it uses dynamic memory. Now we have the binary tree. The binary tree, it can be really helpful for priorities. So it's not exactly built for priorities only, it can be used for other things. But if it's balanced, it can very well be used for priorities. And we have the queue. The queue is, well, the format we're using for accessing the information. Let's imagine we have a line. Stuff comes up here, and stuff comes out here. We cannot take from here, only from the output, right here. So, first in, first out. There's a variation, the priority queue, which is the one we are actually going to manage now. But let's leave that for the heap. Because the heap itself, as I told you, was created for priorities. It uses the format of the queue, which elements come in, and only the highest priority one comes out. The binary tree, because it uses a tree to organize its information. And of course, it uses vector because it's implemented in vector itself. So, these were properly engineered for managing these kinds of stuff, so it's the main structure you're going to see in our program. And well, that should be it for the analysis. Let's go with the next thing.
Well, now that we already know that we are using a heap, we searched for many types of heaps, and we decided of the binary heap. Well, why? Because it deals naturally with the starvation, as JP mentions. The first is the higher priority, and it goes from there out. It also is very it has a tendency of starvation, but that's what we are going to solve. So it is perfect. The consistent type of complexity, because inserting and extracting elements, it has a complexity of all log n. Memory space efficiency, and well, we also thought of the Fibonacci heap, but the binary has a better memory space efficiency, so we thought of binary heap. A is also very predictable, as it is easy to know how it's going to work or what outputs it's going to deliver. And typified complexity isn't very complex, so it is easy to implement. And well, why is our problem different to others? Well, I don't know if you have noticed, but we are talking about starvation. Well, why are we different? Because if we deal with the adaptability and fairness, as we mentioned, every process or every number or every entry has to have a fairness or efficiency. Everyone that goes in needs to go out. Prevention of starvation. Well, we have mentioned very, very much. That's why we mentioned it. Consideration for system efficiency, because everything in the computer or during the running of the program will have a very efficient way of running, as it will be preventing starvation. And it has also a very practical application in task scheduling, as I mentioned, like in the introduction, like in a line for buying tickets, or well, while you do your house chores by organizing yourself. Well, it has many applications.
Well, if you came here to see what the answer is to solve world hunger, you are at the wrong place. But we do have a solution for dealing with starvation inside our program. First of all, we begin with a loop. This loop will go through every single element contained within our vector. For every element, it will increase its age by 1 once an element is, well, this is going to run whenever we remove an element from the AP, just say that. Well, it raises its age by 1. After it raises its age by 1, it will check out all these elements. Right here we put a 10, just to demonstrate. So if the element is 10, it has an age of 10, or a multiple of 10, it will raise its priority. Then it goes back, and for every single element it does that. And once every single element has changed its priority, or let's say the same, we heapify to reorganize and see how it actually looks now, how the heap looks and how it is organized for the elements to come out. So how about we see it in action? Right here, we have Shrek Fest. The concert you want to attend. So how about we add someone to the list? Let's say Edgar. Let's give him a priority.
VIP.
What do you think Edgar is? VIP, MVP, Shrek himself?
Shrek.
Shrek himself. Okay. Now we can see that our heap has some people noted for the Shrek Fest already. There's a lot of priorities there. And if you do the calculations, you'll see that they are completely heapified. There's respect on the priority. And you can see that Edgar is just behind Shrek. How about we take that?
Thank you very much. Thank you, team.
Shrekify.
Shrekify. Okay, as JP said, vector is the best, so you're next.
Let's go.
Please complete this.
Yeah, thank you.
Thank you.
Let's say O1 or O.
What? You said O. You said O1.
Oh God.
I remember. Vector Carrillo. Ready?
Yes.
Go.
Hi, as many of you may already know, I'm Sector, but for the sake of this training, I will introduce myself. My name is Sector Carrillo, and today I will be presenting my project for 10 structures in operating subject. So, first I would like to start my presentation with a simple question. Does any of you have any experience with data analysis? No? Anyone? Okay.
Sorry.
In that case, let me ask you, what do you think is the most important part of data analysis, besides the analysis itself?
Data.
Data. And why? What do you think so?
Because there is no data analysis without data.
But what is the most important process to do before any analysis?
It's really collecting data.
Collecting data and I don't know, maybe the scope fathom what the collection of data is going to be used for, and most importantly, or what I consider is the most important part in my computational problem, the declaration and validation of data. So, everybody knows that there are several methods already for solving this problem. For example, server validation, deployable lists, or log validation. These are just few examples of it. But but as unique as the solutions may seem, they need to be specialized to the system, either its complexity, its scope, or its size, because you can have lots and lots of methods implemented at the same time, but if you don't check for the set of rules, you may you may find yourself in trouble. For example, only one validation method is colliding with another, causing a complete crash. And why is this? Why validating data is important? What is the scope of this project? So, first of all, not everyone has access to last generation algorithms that automatically import data from data consumption into a system. Maybe some people still do it the old way, by hand. What does it mean? That means that misclick or finger mistakes are bound to happen. This not only is prejudicial for the analysis itself, but for the results that you may get. So, in my solution, I created a program with built-in limits, such as n, repeating myself, the Morse code for my last project. In this case, it's going to be scalable. That is another problem with complex systems. We're going to reach a certain roof where you can improve it more, because it's either too costly or you simply need to start doing things. For my solution, I use queues, dictionaries, and lists. But why? As you already know, queues are a dynamic structure. We don't know the size of the input we're expecting. We don't know anything. But this can also be said about arrays. The thing here is that arrays are bit overkill.
No,
I think it was the project.
Okay. Arrays can be a little overkill. Why? We're not trying to access any data in any specific arrays. We're just trying to evaluate the input given by the client and check if there are any foreign characters, foreign meaning, anything besides Morse code. Also, dictionaries. What are dictionaries? Well, for me, it was kind of a sketchy subject because I tend to think of them like a hash table the first time I heard about them. But the thing is that dictionaries, I tend to make some because the dictionaries as the hash tables use a value to key system that allows for a O1 search time, but the difference between the hash tables is that the hash tables are going to create a certain value depending on how many interactions you give them. Like I said, we build, it's scalable, but we're not trying to look for the most for the value that has to do with the most. That's why we have huge and also lists in order to
Ego.
like I said, dictionaries give me a constant time to search for the values that the user may input. Queues, also O1, given that the other operations exist in our queuing, and then the list that is going to store the values of the statistics related to the input. That's it for the presentation. Let me show you. Do me a favor.
What?
Do me a favor.
Yes.
Say the word, something around 5, 6 characters. What do you think?
It's for 10 seconds. Jelly.
Jelly. Let's do it for you. Jelly. Let's say, jelly. Give me a second. What is the E? And then, what is the L? And L. And Y. This.
1 minute. A.
What was supposed to happen partly was to output the word jelly.
Jelly.
I guess this is it before I embarrass myself.
That's it. Thank you. You're next.
Automatically.
Just one question. No. So only one of us can have 10 in each row. Okay.
Only one can have 10.
Or the other one can have anything else for 10. Okay. Thank you.
That is why it's a co-evaluation. Discord.
It's the
Projector.
Discord or that cord?
I couldn't open my Discord on
No.
Those who already finished the co-evaluation, please bring it to me.
okay.
Thank you. Thank you. Ta-da! Yes. Thank you. That side there's a, no, the white one has a button with the icon of input. No, that's enter. That one. So you can select, I think it's HDMI 1 with up and down arrows. That's it. And now enter. So it's the second one. Oops. Press enter. Thank you. That's it. Ready?
It's aesthetic.
Go.
This is my final presentation, now by myself, because I was speech trained. I can promise a political speech like 80 people. So, the super related problem that serves as a foundation for my project was that when working with large data sets, it is important to consider the storage space and the retrieval speed for data, since when data sets continue to grow in size and complexity, problems may arise arise around the management, retrieval, and storage of data, like for example, we need more space or physical space for storage needs, or the time or longer times to process data. And for this, you will need data management that can handle increasing volumes of data, and this can be solved and without it losing the integrity and accuracy of the original data. And this can be solved through data compression. Data compression involves the reduction of size of data, so it can take less space in storage, and it will have a faster retrieval time. And also this achieves it without losing the integrity of the data. And because of this, it can be applied to a wider range of domains, because it will reduce the costs and resources needed to process, retrieve, transmit, everything that has to do with data sets. And for example, it can be used in databases and cloud storage to reduce the physical space needed to store the data, and in networking and transmission to reduce the time it takes to process, retrieve, and transmit the data. And it goes hand by hand with data analysis, like it was explained. And well, for the solution, the main features of my solution is that it works with text. So, for example, you put a text file that can be CSV or another text file, and it will separate each character in the text, and it will count how many appearances it has on the text. Then, depending on the frequencies, it will assign them a code, a binary code. Longer codes will be assigned to characters with lower frequency, and shorter codes will be assigned to characters with higher frequencies. And this is used in order to encode the message and to decode the code. And that is used to decode and prevent its well, the data structures that I used for this implementation of the solution were trees, heaps, and caches. The tree is basically the foundation of the solution, since for encoding and decoding, we will need to traverse the tree in a way to assign the codes. For example, if this this node is the character A. To give it its code, it will be left, we assign it a 0, and then left again, we assign another 0, so the code will be 0, 0. And well, the tree was chosen because it's the simplest thing to implement this, because of the traversal, because this can also be applied with vectors, but it will be more complex and harder to understand. And since trees have the complexity of logging in the operations, it's another plus. Another thing why I use trees is because of recursion. Recursion makes the code very easy to understand and read. And then the heap was used to organize the characters depending on the frequencies in order to build the tree. Because to build the tree, the algorithm follows that to build the tree, you need to start at the bottom and combine the characters with the longest frequencies, and then it will reach the root. And the heap also can be implemented. Well, the algorithm that the heap state can also be implemented by other data sources, but then again, this is the way simpler. And also it has a complexity of log n. And finally, I decided to use hashes because they make it very simpler to associate the characters with their respective frequencies and codes. And because the algorithm and the solution I implemented uses a lot of search operations, and well, the hashes will fit perfectly since they have a constant search operation. And well, that's it for the presentation, where I will explain more or less how the encode and decoding works. So let's quickly encode. Well, first you need to create the roots of the characters. Once you have the tree fully constructed, you can traverse the tree and see what is the code for each character, and you can store it in the hash. So when you decode it, you can just go for each character in the text and search that character in the hash and replace it with the code. And for decoding, you will start at, well, you will go for each character in the encoded text and traverse the tree from there. So if the first character is a 0, it will go left, then if the second one is 1, it will go right, and until it reaches a leaf, it will replace that code with the character. And now for the code itself. So here it asks for the text, or you can read the program. So I'm going to introduce the counted monologue. And here are there's a table with the frequencies of each character. And as you can see, the characters that have a higher frequency receive a shorter code, while the ones with a lower frequency receive a longer code. And here will be counts monologue encoded. Here it is encoded. And this can also work with CSV files, so you can see it.
CSV. Dataset.
Yes, this one is longer. There again, you can see this. And the encoded text, and finally encoded text. So that's it.
Thank you, Cedric. I think we're done. No? Maybe? Yes. Thank you. Yes. Thank you. Thank you. Ready? Set.
Don't look, close your eyes. That was
Ready, set. There we go.
Andrea and me are going to present you our final algorithms and data structures projects. So we state with our computational problem was that works with undo and redo functions, but these functions are not enclosed when we work with documents. You can also work with them in videos, in databases, in graphic design projects, in websites, anywhere you want to delete something and then you want to get it back, you can work with these functions. For example, in video editing, if you edit the whole part of the video and then you want to delete it and then take it back, you use undo and redo. But for our approach, we're going to focus on external. So the last time we were really focused on deciding which data structure was the best for implementing undo and redo, and we ended up always with stacks because of its natural behavior with info. It works with last in, first out. So what we were missing is that we would also need to choose the data structure that we're going to implement the stack with. And the stack was the perfect solution for our problem because of the simplicity of HTTP, the simplicity, and the memory management because of it doesn't use pointers, so it was efficient in memory.
well, that's not my part.
For selection, we were deciding between implementing the vectors or linked list, and during the analysis, the implementation of the stack is either with vector or linked list, depending on the complexity of the problematic. For example, if you're working with a large video, you need to handle a lot of memory. And a lot of memory is easier to handle with linked list because of the efficiency to grow in memory. In vectors, you have selected blocks of memory, so it's not as easy as with linked list to work. But also, linked lists work with pointers and all that, so the complexity time is longer. And for our approach to the problematic, vector is the best option because we are not working with a large amounts of data, we are working with text. So we just enter the vector, put the text, and then push or pop.
Well, now here you can see our kind of flow chart of how our solution implemented. First of all, we need a sentence. That's so easy. We want to redo or undo. We need a sentence, a group of words, a paragraph, words. Then we have to decide what to do next. We can undo, redo, or stop the program. Let's suppose we want to undo. First of all, we have to ask if it can be with us, because if there's no words, you can't do anything. Yeah. If there's no words, it is supposed to ask again, or you have to do another thing. And if it's undo, you have to store that word you want to undo, and then remote. Now, let's suppose we want to redo. We have to ask if something has been undone, because if it hasn't, we can redo. It's the same logic as the undo. Here, it works connected with the undo. As here we store the word, we undo, have to press that word to redo, and add it. If it's correct, if not, it goes back. And then let's suppose you ask for it, and now we don't have any change. We end the program, and the sentence has to stay as the way it is. Well, now let's see in a how can I say create diagram
we use a get line to get that sentence. Then we divide it in words and add it to store them in a vector. And then each word will be added to our stack or to our variable to save the sentence with the edit function or method. Well, and this is we wanted to make the program a little bit more dynamic. We didn't want it only to put some words and that's example. So we implemented it this way. First of all, we made the ch variable, which is only to choose that. It doesn't have other points. Then we start a while that will run until ch is 3. As we can see here, 3 is the ending of the program. So it is ending here. Whoop, and okay, first it checks if it's 1 or if it's 2. It doesn't matter when we start, mainly because it's 0. So it can run and do nothing like that. This works after this part. So I'll explain it in a few moments. This is the actuals. It prints the text or the sentence you added and ask what you want them to do next. If you want to do, it goes here at DCH and does this. And after doing this, it changes or initializes again the outcome. Like sets again its value to 0. And works and works and works and works until it's 3. And if you add another number here, it asks you in a really kind of way. Please enter a number from 1 to 3. And that's it. Well, the undo and redo methods are stats, basically. Now, exciting part. Just run it with the input. Yeah.
Enter your text.
Your text. What do you want it?
Breakfast was the best.
Okay. That's your sentence. What do you want?
Let's undo.
And we have the shirt test. What's it?
Let's redo.
Redo.
Redo again.
I'm going to read.
The best.
Okay,
We undo